In 1965, engineers outlined a proposal for a helicopter so massive its rotor span was longer than a 120-meter soccer field. And its mission wasn't to carry people or cargo. It was meant to catch falling rocket boosters in midair before they hit the ocean. In this video, we'll explore how the Air Tug concept aimed to rewrite rocket recovery, compare it to SpaceX's 2025 landings, and examine the flaws that stopped it before construction began. Along the way, we'll unpack the physics, the logistical hurdles, and why the 1960s had the funding to even consider such an idea. The 1960s space race spending surge. At the height of the Apollo era, NASA operated with a level of financial backing it hasn't seen before or since. In the mid-1960s, the agency's budget reached roughly 4 to 5% of total U.S. federal spending, far larger than anything allocated in recent decades. That share reflected more than just enthusiasm for spaceflight. It was a direct product of Cold War urgency, where the moon became a public scoreboard in the competition with the Soviet Union. Bold, high-risk concepts were not only tolerated, but actively encouraged if they promised even a marginal advantage in the race for visible milestones. This environment created opportunities for proposals that, in other contexts, would have been dismissed outright as impractical. By 1965, the Soviet Union's lead in early space firsts, from placing the first human in orbit to achieving multiple crewed missions, had put public and political pressure on U.S. leadership. The White House and Congress were determined to fund projects that could close the gap quickly, even if doing so meant stretching the boundaries of what aerospace engineering had accomplished. There was room in the budget and the political appetite to explore ideas that pushed conventional limits. It was in this climate that Hiller Aircraft Company pitched its Air Tug concept to NASA. The idea was straightforward in principle, but extreme in scale. A rotorcraft large enough to intercept and retrieve an expended rocket stage before it ever touched seawater. Hiller's leadership had a track record for experimental rotorcraft, but nothing close to the size and payload demands of this proposal. Under normal circumstances, a design like this might have been filtered out after preliminary cost reviews. In the mid-60s, when NASA's agenda prioritized speed, reusability, and any breakthrough that could reinforce U.S. dominance in spaceflight, the concept was granted serious evaluation. Part of that attention came from a genuine cost-saving incentive. Each Saturn V first stage represented years of skilled manufacturing, and in modern terms, costs in the billions. Once expended, these massive structures fell back to Earth and were lost to the ocean. Reusing even a portion of that hardware promised significant budget relief, savings that could fund additional launches without increasing overall spending. NASA's engineers and administrators understood that in a high-profile, deadline-driven program like Apollo, every recovered component translated into more flexibility and more bargaining power during budget negotiations. The Air Tug's pitch fit neatly into this equation. Midair capture would, in theory, eliminate the saltwater corrosion and lengthy refurbishment processes associated with sea recovery. Swift retrieval to nearby facilities could shorten turnaround times, helping to keep the tight Apollo schedule on track. The savings and efficiency gains, if achievable, were enough to justify funding design studies and simulations, even if the odds of reaching an operational aircraft were uncertain. NASA's willingness to explore the Air Tug was part of a broader pattern during its peak funding years. Ambitious concepts were circulating for nuclear-powered spacecraft, kilometer-scale orbital platforms, and interplanetary missions, all explored in parallel with the lunar program. These studies often stopped short of becoming hardware, but the fact they were funded at all speaks to the uniquely permissive environment of the period. The goal wasn't to build every idea to completion, but to identify options that could confer strategic and symbolic advantages if they proved technically feasible. This broader atmosphere also benefited contractors. With multi-year budgets that sustained large teams, aerospace firms could invest in speculative R&D without the immediate need for market viability. Universities received research grants directly tied to such projects, and specialist knowledge flowed into NASA's contractor network. In that sense, the Air Tug was both a product and a beneficiary of a competitive ecosystem designed to reward pushing the limits. even if the endpoint was only a paper study. By the time Hiller's massive helicopter concept reached NASA's desks, booster recovery itself wasn't a new discussion. It was already recognized as a potential cost saver. What was different was the proposed method. Instead of pulling a spent stage from the corrosive ocean, the Air Tug would meet it in its slow descent under parachute and return it to land almost immediately. That leap in recovery strategy, combined with Apollo-era funding conditions, gave the proposal an opening unlikely to have existed at any other time in NASA's history. Understanding this financial and political backdrop is key to understanding why an idea as extraordinary as the Air Tug made it into formal study. It was never just about engineering for its own sake. It was about meeting a national objective with the tools and the budget that were available. That mindset valued speed and spectacle as much as efficiency, and the Air Tug promised all three if it worked. But before such a machine could be justified, NASA had to weigh it against the recovery practice already in place, one that seemed sensible on paper, yet carried its own hidden costs. That existing approach would become the baseline against which the Air Tug's feasibility was measured. The problem with ocean landings. In the early Apollo era, engineers followed a standard plan for recovering any part of a spent booster. Let it descend under parachutes and come down in the ocean. The reasoning appeared sound. Once a stage's engines shut down and separation occurred, gravity took over. Water, being far more forgiving than solid ground, could spread the force of impact, lowering the risk of catastrophic breakage. Landing something as large and massive as a Saturn V's first stage on land was simply not an option. Parachutes alone couldn't slow it enough to survive the jolt without structural ruin. Recovery parachutes were designed to deploy in stages, easing the booster through different phases of its fall. In the final seconds before splashdown, they cut the descent speed to a fraction of what it would have been otherwise. This limited the sharp decelerations that might buckle a frame. For a program under pressure to preserve as much hardware as possible, it looked like a reasonable compromise when compared to the near-certain destruction a ground impact could bring. But the ocean introduced a different set of challenges, ones that quietly undermine the case for reuse. Seawater is a highly active corrosive, especially against the aluminum alloys and mixed metal assemblies central to a rocket structure. Salt crystals rapidly embedded themselves into joints and seams, and galvanic reactions began wherever dissimilar metals met. Even careful rinsing on board recovery ships couldn't undo the damage set in motion during those first hours in the water. Protective coatings breached during launch, or staging left bare metal even more vulnerable. Corrosion wasn't the only problem. Splashdown itself, despite being soft by comparison, still hit with enough force to dent outer skins or warp internal frames. The angle of entry was difficult to control. Side impacts or uneven contact with waves could twist bulkheads and misalign structural elements. Much of this damage wasn't visible at a glance, but it could weaken the stage for any future flight. By the time a recovered booster reached a refurbishment facility, thorough disassembly and inspection were needed, not only to address corrosion, but to detect stresses hidden beneath the surface. All of this added cost. Restoring a saltwater exposed stage required stripping and replacing many components, flushing or remachining systems contaminated by brine, and often rebuilding structural sections from scratch. For critical areas like engine nozzles, turbopump housings, or separation mechanisms, even minor corrosion could push them beyond safe tolerances. In practical terms, the expense of this work often rivaled or exceeded the cost of simply building a new stage. Operational realities worsened the equation. Retrieval was far from instantaneous. Ocean recovery demanded coordinated ship deployments to remote splashdown zones, tracking floating hardware by parachute beacons and visual sighting. Weather, heavy seas, and location uncertainty turned some recoveries into drawn-out operations. Each extra hour in the water meant deeper salt intrusion into hinges, seals, and wiring channels. With staging events occurring far offshore, even after retrieval boosters spent days in transit back to port, exposed to spray, humidity, and physical handling. all compounding the initial seawater damage. Compounding the issue, broad recovery zones meant recovery vessels had to cover large areas, often without continuous positional data. In the 1960s, without global real-time tracking, any delay in pinpointing a stage risked it moving further from optimal pickup points or worsening in condition while drifting. Although outright losses of hardware were rare, the unpredictability and potential for delays eroded confidence in ocean landing as a reliable, cost-effective recovery strategy. The corrosion and impact stress combined to substantially reduce the service life of components. Even if individual parts could be salvaged, the integrity of the stage as a whole was often compromised. Inspections would reveal enough damage to make reuse impractical, except for limited subsystems. That meant sea recovery had shifted from a strategy for recapturing large hardware intact to a method of reclaiming smaller, valuable parts. Hardly the savings originally envisioned. For NASA in the Apollo years, this was more than a technical irritation. It was an economic and scheduling liability. Expending time and money on refurbishing ocean-soaked stages could slow launches and siphon resources from other mission priorities. In a program where political pressure demanded both speed and high-profile success, such delays and costs were difficult to justify. These experiences shaped a clear conclusion. The softer landing the sea provided came at a steep price. Corrosion, hidden structural stress, slow and weather-dependent retrieval, and mounting refurbishment costs combined to limit or nullify the financial benefits of recovery. Avoiding seawater was the principal benefit the Air Tug promised. By catching a stage in mid-descent before it touched the ocean, engineers aimed to sidestep the cascading damage and expense inherent in splashdown recovery. A solution like that had to overcome enormous technical hurdles, but the potential rewards were compelling. Booster stages in clean, dry condition, flown directly to controlled storage or refurbishment with minimal delay, preserving much of their designed lifespan. This, more than any novelty of the idea, was why proposals for airborne recovery earned serious attention at NASA's peak of ambition, and the concept being studied at Hiller Aircraft envisioned doing it with a machine on a scale unlike anything the aviation world had ever seen. The monster in the sky, Air Tug design. Hiller's proposed Air Tug design revolved around a rotor system of unprecedented scale. The plan called for a rotor disc about 400 feet in diameter, roughly 120 meters, wider than a football field is long. No helicopter before or since, operational or experimental, has approached such a span. That size wasn't about spectacle. It was dictated by the lift requirements for a Saturn V first stage. Even depleted of most fuel, that stage would remain a massive, ungainly cylinder, tens of thousands of pounds in weight, with a surface area ready to catch and amplify turbulence. The only way to control and carry such a load in the air was with an immense rotor area generating stable lift through the chaotic conditions of mid-descent interception. The approach to driving this vast rotor differed from the norm. Conventional helicopters route power from engines through a mast and gearbox into the blades, but at this scale the torque loads and gearbox mass would become prohibitive. Instead, the leading idea on the table was to mount small turbojets or ramjets at each blade tip. Their direct thrust would spin the blades without the need for an oversized transmission. Proposals explored one or even two tip-mounted engines per blade. With sufficient power, the rotor could turn at around 60 revolutions per minute, only one full rotation each second. That speed sounds slow until you consider the sweep. The outermost parts of the blades would be moving at velocities approaching the speed of sound at sea level, triggering aerodynamic effects unlike those in smaller designs. Supporting the rotor meant scaling up the rest of the aircraft. Hiller's figures suggested an empty weight near 450,000 pounds and a gross takeoff weight on the order of 1 million pounds. Much of that came from the sheer structural mass needed to bear rotor loads and to carry a suspended payload both heavy and physically awkward. Unlike a standard sling load, the first stage was tall and narrow, shifting in response to gusts and its own inertia. The Air Tug had to manage all those forces while maintaining control during complex maneuvers. target payload capacity, was estimated just above 50 tons, about 100,000 pounds when including residual propellants, parachute lines, and the rigging required to lock the stage into place. Meeting that performance target restricted almost every other design decision. Sustained, high-thrust operation of the tip jets during a recovery demanded significant onboard fuel stores. Fuel weight itself ate into lifting margin, so every pound in the airframe or onboard systems had to be justified against payload capacity. Even with operations planned close to launch or recovery bases, range could not be traded entirely for lift efficiency. The Air Tug still needed enough final phase maneuvering reserve to circle, align, and if needed, make repeated capture attempts. The fuselage arrangement was shaped by the capture mission, rather than the sleeker central body of a long-range transport. Draft layouts depicted a frame built as much for clearance and stability as for forward speed. Two downward-sloping booms extended, alongside an open midsection, forming a cavity through which a descending stage could settle without striking the fuselage or blades. These booms doubled as mounting points for grappling gear and as partial shields to cut cross-flow around the payload once restrained. Designing a rotor 400 feet wide introduced aerodynamic and structural issues wholly different from those in any other helicopter program. First was tip speed. At 60 RPM, each blade tip would travel over 1,200 feet per second, bordering on the transonic regime. Compressibility effects at that speed would drive sudden spikes in drag and generate shock waves, reducing lift efficiency and punishing the blade structure. Second were the centrifugal forces. At that radius and rate of rotation, outward pull on each blade would reach extraordinary levels, adding massively to the hub's load and forcing every component in that central assembly to be heavy, robust, and precisely engineered. Third was the lack of materials and manufacturing methods in the 1960s capable of achieving the strength-to-weight balance those conditions demanded. Blades light enough to keep centrifugal forces manageable often would not withstand continuous high-load transonic operation. Blades built strong enough for those loads risked bringing the disk's mass beyond acceptable limits, while tip-jet propulsion removed the mechanical torque that would otherwise have to be countered by a tail rotor. That advantage gave way to new problems at the hub. Here, engineers still had to manage the combined load paths of blade centrifugal pull, vertical lift forces, and the swinging mass of the payload, plus the aerodynamic moments from the forward flight needed to rendezvous with the booster. Any failure in that complex assembly would not be survivable for crew or cargo. Still, scale drawings and preliminary simulations suggested that, in theory, such a helicopter could get off the ground and lift what the mission required. Achieving it in practice depended on extremely narrow performance margins. Even moderate gusting, unexpected payload movement, or heat-weakened materials could rob the system of the responsiveness needed to keep such a large recovery stable. In that regard, the Air Tug was as much a study in the limits of rotorcraft physics as it was a design exercise in airborne logistics. In sheer dimensions, this proposal overshadowed anything airborne at the time. The Soviet Mi-12, record holder for the largest helicopter ever flown, spanned 220 feet rotor to rotor, barely half of what Hiller outlined. Imagine parked in a stadium. The Air Tug's blades would overhang the seating by a wide margin. Even through 2025, no operational rotorcraft reached that scale. The largest in service today stand well under half that diameter, with lift capacities only a fraction of the Air Tug's target figures. Advances in materials, computer-aided control systems, and turbine performance have not yet brought such a machine into the realm of flight test. Had it been built, even as an experimental vehicle, the Air Tug would almost certainly have claimed records for both rotor span and gross weight in a single rotor helicopter. Its function placed it closer to a flying crane or specialized gantry than to any transport model, applying known lift principles, but magnifying them to a point where every design compromise became critical. On paper it read like a brute force solution, but the physics had other ideas. The next question was how this oversized helicopter was actually meant to perform its job. The recovery plan required precise timing and maneuvering from the moment a stage separated until it could be captured in flight. And the Air Tug's engineering choices only made sense in light of that demanding sequence. The Midair catch concept. The Midair catch plan started with a very specific sequence from the moment a Saturn V's first stage separated. After engine cutoff, explosive bolts would release the stage, and it would fall freely for a short interval. Then a series of parachutes would deploy in 2 steps, small drogue chutes first, to steady and slow the cylinder, followed by main canopies large enough to produce a stable vertical descent. Once under main parachutes, the booster would enter a defined interception zone, an altitude band where the Air Tug could close in and match its motion. The loiter point for the helicopter was projected at around 15,000 to 20,000 feet, while the capture attempt was expected to occur at approximately 10,000 feet. Below about 5,000 feet, the time margin vanished, and the chance of avoiding a splashdown effectively ended. The Air Tug's crew would already be in the air before stage separation, orbiting well clear of the predicted drop path. Beacon transmitters on the booster's parachute rig, along with ground and ship-based radar, would feed positional updates in real time. These guided the helicopter toward an intercept point without wasting fuel or maneuvering room. The enormous rotor disc limited abrupt movements. Sharp turns or sudden climbs risked uneven lift and instability, so the approach would be gradual, keeping the entire aircraft aligned with the descending booster. At around 10,000 feet, the crew would initiate the first intercept run. This altitude offered enough dense air for strong lift, while leaving thousands of feet of margin if the first try failed. The booster, descending under canopy at roughly the speed of a fast jog, still demanded precise control. The helicopter had to match both vertical rate and horizontal drift. An object hanging beneath several parachutes rarely came straight down, and wind could yaw or sway it unpredictably. The Air Tug would keep formation alongside, making fine lateral adjustments while staying clear of the parachute lines. The capture gear, a retractable mast and grapple extending from the fuselage cradle area, was designed to hook into reinforced fittings in the parachute rigging rather than the booster itself. By targeting the rigging, the crew avoided having to align perfectly with the stage's axis. Once the grapple locked, a winching system would draw the booster upward until it hung, suspended roughly 700 feet beneath the helicopter, nested in its cradle zone for the flight home. If the first capture attempt failed, whether due to a miss or unstable canopy behavior, pilots would peel away, reposition, and try again. The descent rate under parachutes meant there was realistically time for only 2, maybe 3, passes before the stage dropped below 5,000 feet. At that point, the remaining seconds before impact were too few to set up a safe run. Abort procedures would then kick in, and the booster would be left to splash down for conventional retrieval. Multiple attempts carried their own hazards. A helicopter this large produced significant downwash and turbulence, which could disturb the parachutes of a drifting booster. Simulations suggested that approaching slightly off-axis, then sliding into position, reduced the effect. But in higher winds, the disturbance could increase canopy oscillations instead of settling them. Pilots had to weigh whether another attempt risked entangling the load or producing swings too severe to control even if capture succeeded. Timing was tight. Each intercept pass spanned tens of seconds plus repositioning time, so every miss consumed a measurable chunk of available altitude. Crews expected that most successful recoveries would happen early in the sequence. By the last possible attempt, unstable canopy motion and rotor wash disturbance made success unlikely. Simulations in ideal weather indicated the concept could work reasonably well. Steady winds below about 15 knots, smooth canopy behavior, and good visibility all supported capture. But once crosswinds exceeded that threshold or gusts became erratic, performance degraded sharply. In higher or variable winds, canopy drift became too unpredictable, making it unsafe to keep the rotors clear while moving in close enough to latch on. Under those conditions, the odds of securing the booster dropped close to zero. Even when conditions were favorable, there were design dependencies that could end mission. The parachute rigging not only had to slow the drop, but also withstand a sudden lift load from the Air Tug. A failure during that instant could send the booster plunging away, forcing immediate evasive maneuvers to avoid collision. And the moment of capture shifted the helicopter's weight distribution abruptly. If not anticipated and countered at once, that shift could lead to oscillations in the suspended load. Once swinging began, the risk of damaging forces on both the booster and the helicopter's structure increased. Pilots would stabilize the load by easing power and small cyclic inputs until the booster hung directly beneath the fuselage, motionless in the vertical plane. This step was critical. A pendulum as massive as a rocket stage was difficult to stop if it gained momentum. Only after the load steadied could the flight engineer set power levels for efficient cruise, mindful that fuel burn peaked when hauling the full suspended weight. Planning an actual recovery route layered more complexity onto the flight profile. Ground tracking predicted descent corridors based on telemetry from launch, but even minor trajectory variations could shift the drop zone away from expectations. The splashdown area for a Saturn V's first stage was typically more than 350 nautical miles downrange from a launch site. For the Air Tug, that range meant it could not realistically return to base after capture unless supported by large floating platforms or barges stationed closer to the interception zone. Without such staging, operational return times under load would be impractical, especially in adverse weather. The Midair catch aimed to replace the randomness and corrosion risk of ocean landings with a controlled, point-to-point airborne recovery. Every phase, descent tracking, approach, grapple, and load stabilization, played out inside a narrow altitude window. Success depended not just on technology, but on weather, timing, and crew precision under pressure. When those factors aligned, the system offered the possibility of returning a stage in clean, dry condition within hours. When they did not, the mission's viability collapsed quickly, returning the booster to the sea and erasing the potential benefits. The limitations of the capture operation, from the narrow altitude margins to the long distances downrange, pointed toward a bigger truth. To make the Air Tug capable of such a task meant confronting engineering constraints that were not only unusual, but in some respects unprecedented for a rotorcraft. Those constraints would soon become some of the most serious obstacles to moving the design off the page and into the air. Engineering roadblocks. One of the clearest technical limits in the Air Tug plan arose from the rotor's sheer scale. At around 1 full rotation per second, the tips of its proposed 400-foot blades would be moving close to the speed of sound. In smaller helicopters, designers already worked carefully to keep tip speeds away from this transonic range because the moment airflow begins to compress near the tips, drag rises sharply. Shock waves can form along the leading edges, creating vibration, raising stress on the structure, and increasing fatigue rates far beyond normal expectations. For something this large, operating at the lift needed for booster recovery meant those conditions would be present much of the time. This fed directly into another design constraint: material strength versus weight. Blades were not just aerodynamic surfaces. They were structures loaded continuously by forces trying to fling them outward from the hub, with hundreds of tons of equivalent pull. The stronger you made them, the more weight you added. The heavier they became, the stronger and heavier the hub and mast had to be to survive the centrifugal load. Adding mass at the top of the aircraft increased demands on the lift system, cutting into the payload margin. Even with late 1960s advances in aluminum alloys and early composites, finding a balance where the blades were strong enough, light enough, and still durable enough for repeated missions was not straightforward. The payload created its own unique handling problem. Conventional sling loads are relatively compact for their weight and hang close enough that shifts in the center of gravity can be corrected quickly. A Saturn V first stage, by contrast, was both long and aerodynamically unstable. Once hooked and suspended far beneath the fuselage, it would behave like a long pendulum with a large surface catching any gust or turbulence. Even rotor wash from the Air Tug itself could set it moving unpredictably. Managing that motion would require constant, fine control in pitch and roll to keep both the stage and the helicopter in stable flight, something never tested at the weight and dimensions involved here. Attempts to tame that load included ideas for partial fairings or frames to shield it from crosswinds. But anything added below also added weight above, tightening every other design margin. Aerodynamic shielding also could not remove the mass moment effects of such a long suspended object. Once it started moving, it wanted to keep moving. The longer the load, the more slowly any corrective input could stop the swing, and the worse the forces if it reached maximum amplitude. Noise and vibration formed another barrier. Large rotor systems are inherently loud, but the tip-mounted jet engines proposed here compounded that. Historical records from other tip-jet rotorcraft, like the Ferry Rotodyne or Hughes XH-17, described noise levels so high they limited where these aircraft could operate. The Air Tug's projected combination, low-frequency blade beats plus multiple high-frequency jet exhausts at the tips, would likely have produced noise intense enough to carry for many miles. It would also have propagated significant acoustic vibration through the structure, feeding into fatigue cycles for the blades and airframe. Maintenance projections reflected these stresses. Tip-jet helicopters historically suffered heavy erosion at blade tips, high thermal loads near the engines, and greater where on rotating joints due to vibration. Early Air Tug studies expected this machine would need far more frequent inspection and parts replacement than a conventional heavy-lift helicopter, eroding the financial appeal of booster reuse. Analyses drawing on tip-jet experience suggested an operational life for blades and other rotating components that would be unacceptably short compared to established rotorcraft, driving up downtime and costs. Replacing a single blade on a machine of this size would not have been a quick turnaround job. Each blade would have been a large precision component with fuel lines for its tip engines, internal controls for pitch adjustment, and structural reinforcement running nearly its entire length. Any swap would require major lifting equipment, extensive on-ground labor, and potentially days out of service. The more often such replacements were needed, the harder it became to build a reliable recovery schedule. In condensed form, the main engineering roadblocks came down to three interconnected constraints. First, aerodynamic and sonic effects at the blade tips imposed constant stress loads and efficiency losses that no known rotorcraft design had handled at this scale. Second, the strength versus weight cycle meant each solution for structural integrity added mass aloft, cutting into payload capacity and stability margins. Third, the historical experience with tip-jet helicopters pointed to exceptional noise and ongoing maintenance demands that would push operational costs high enough to wipe out projected recovery savings. Each of these factors linked to the others. Lowering tip speed to reduce sonic drag required bigger blades or higher pitch settings, both of which increased hub loads. Adding structure to contain the swinging payload brought more weight, further stressing blades already near their operating limits. Attempting to damp noise could mean reshaping blades or reducing jet thrust, which eroded lift efficiency. There was no easy change that didn't cause knock-on effects somewhere else in the system. Design teams at Hiller tried adjustments in blade construction, tip jet placement, and load attachment geometry to relieve some of these pressures. On paper, these trade-offs could keep performance within its targets, but only just. As soon as real-world factors entered gusty conditions, unpredictable canopy behavior, or just the wear and tear of repeated flights, the operational envelope narrowed sharply. The Air Tug could be drawn to meet the mission's physical demands, but keeping it there safely and affordably over time was another matter. Those problems weren't just hypothetical. They stacked in a way that made cost and reliability fall apart in long-run calculations. And the financial impact of these technical limits only deepened when attention shifted to where recovery missions would actually take place. The range problem, one of the most serious operational constraints, had nothing to do with lift capacity or flight control. It was about location. A Saturn-class first stage didn't simply drop just offshore. It fell roughly 350 nautical miles downrange, about 650 kilometers from the Florida coast. That splash zone was fixed by the physics of the launch trajectory. For the Air Tug, this meant a land-based intercept was neither practical nor safe. Even with generous performance estimates, the aircraft would still have to cover hundreds of miles to reach the drop, arrive early enough to set up for an intercept, carry fuel reserves for potentially multiple catch attempts, then haul a multi-ton booster back at reduced cruise speed. By the time the crew reached the target area from a base ashore, most of those margins for fuel and safety would already be eroded. The logical workaround was to base the helicopter closer to the falling stage. The most direct solution was a sea-based forward platform, positioned near the predicted drop corridor, so the Air Tug could be airborne within minutes of booster separation. On paper, that positioning solved the range issue, but it immediately created a separate layer of engineering and budget problems. Where exactly would such a platform come from, and how would it handle a helicopter of unprecedented size? Neither conventional aircraft carriers nor the helicopter assault ships of the 1960s were built to accommodate a rotor span on the order of 400 feet. The tips would extend far beyond the beam of even the largest carrier flight decks, creating hazards in rolling seas. Weight posed another challenge. At gross takeoff weight, an Air Tug could approach 1 million pounds. Any deck able to support it during takeoff, landing, and servicing would require major reinforcement. And that assumed enough open deck area could be cleared for safe operations without interference from other ship functions. Design studies quickly pointed toward a dedicated platform built solely for Air Tug deployment and recovery. Such a vessel would need a flight deck large enough to operate the helicopter without rotor overhang into open water. It would require a sheltered hangar tall and wide enough to house the rotorcraft for maintenance, including blade changes plus storage for unique spare parts. Large fuel reserves and pumping systems would be essential to service the tip-mounted engines between operations. And all of that would have to be packaged aboard a ship stable enough to operate in the open Atlantic while holding precise station for launch-linked intercept windows. In condensed terms, the platform would have to be on station and fully operational at the right moment. It would need to be the size and stability class of a carrier or oversized barge to handle the Air Tug safely, and it would come with high recurring costs, while introducing a single point of failure for the whole recovery plan. If that vessel were down for maintenance, caught in bad weather, or forced to leave its station, recovery capability for that launch would vanish with it. A carrier or barge-scale ship was a big ask. Beyond the build itself, it would need long-term crew accommodation for aviation technicians, deck crews, engineers, and support staff. Navigation and communication suites would have to integrate seamlessly with NASA's tracking network. The propulsion and positioning systems would need to match changing launch azimuths and relocate as mission profiles shifted. From fuel resupply to scheduled yard work, the scale of upkeep on such a vessel would rival that of major naval units. Operating costs quickly became central to the conversation. Every day at sea would consume fuel, pay wages, and wear down machinery, whether a launch was scheduled or not. That meant year-round expenditure for an asset used relatively infrequently, an awkward fit for a cost savings program. Even if the Air Tug itself performed flawlessly, reducing refurbishment costs per booster, those savings could be wiped out by the fixed cost of keeping a massive offshore platform ready. Risk concentration was another concern. Land-based recovery could spread multiple helicopters across existing airfields, sharing parts and crews. A single giant platform, by contrast, created a single point of operational vulnerability. One breakdown in propulsion, one failed crane, or a weather diversion could scrub a carefully timed recovery attempt. Each missed intercept reduced the average savings across missions, eroding the entire economic argument for the system. Timing added more pressure. Apollo launches followed narrow windows dictated by orbital mechanics and mission timelines. If the platform was not on station, or if weather prevented Air Tug launch, the recovery plan failed for that flight. Delays were costly, and adding complex offshore logistics into the critical path of a moon mission was viewed warily by planners. Alternate deployment patterns were briefly brainstormed. One suggestion was to scatter smaller support vessels across the descent corridor, each serving as a forward refueling or staging node. Another was to preposition multiple Air Tugs in dispersed locations, so one would always be within reach. But smaller ships couldn't support the helicopter's footprint or heavy maintenance needs, and duplicating the aircraft multiplied already daunting procurement and running costs. In either case, the core range problem morphed into a proliferation of other logistical and financial difficulties. The deeper planners looked at it, the clearer it became that solving the range gap was not just about fuel tanks and flight planning. It was about building and sustaining a floating airbase the size of a capital ship. And a capital ship brought capital ship expenses. The ship would need to be enormous, carrier or barge-sized, which undercut the very savings the Air Tug was designed to deliver. If the recovery base costs nearly as much as the hardware you want to save, is it still worth doing? By the close of the decade, this question carried weight beyond the Air Tug studies themselves. NASA's attention was beginning to swing toward other visions for reusability, ones that promised political appeal and a different path to long-term cost reduction. Those competing concepts would soon reshape internal priorities and define the next stage of America's thinking about reusable launch systems, alternate paths, and space shuttle influence. By the late 1960s, NASA's focus was tilting away from helicopter-based booster recovery and toward a different vision of reusability. Apollo's primary goals were about to be met, and attention was turning to what kind of spacecraft would follow. For decision-makers, the forward path was less about catching detached rocket stages under parachutes and more about designing an entirely new launch system that could depart and return in one piece. That concept, eventually refined into the Space Shuttle, promised a fully reusable crewed vehicle carried aloft by boosters, capable of gliding back and landing on a runway. This idea had undeniable political and public relations advantages. A winged orbiter landing on a strip like a conventional aircraft was easy for non-engineers to understand and to picture in headlines. It projected an image of routine, pilot-controlled missions and suggested that spaceflight could move toward airline-style operations. Compared to that, the Air Tug's process, launch coordination, downrange positioning, catching a swaying booster under massive rotor blades, looked complex and unfamiliar. Even if it could work reliably, it was harder to sell as the emblem of the next space era. Inside NASA, Midair capture was only one of several post-Apollo recovery concepts being studied. Other proposals included landing spent stages back on shore with parachutes, equipping them with flotation gear for direct towback, or adding wings and jet engines so boosters could fly themselves home. All of these retained a multi-stage expendable architecture, which by then was seen as a specific solution to the Apollo lunar program, not necessarily the foundation for future decades. The shuttle concept, by contrast, was pitched as a long-term transport platform. It could serve military payload delivery, satellite deployment, and space station resupply with one recurring vehicle type. That broader role matched wider policy interests and made it easier to win support at the national level. Budget realities sharpened the divide. Apollo's final missions were already trimming costs, and NASA leadership knew the agency's share of federal spending would be far smaller going forward. Only a limited number of major programs could proceed. Pursuing multiple recovery experiments risked fragmenting effort and exhausting funds before any system reached operational maturity. Once the shuttle started gaining political traction, it absorbed a growing share of funding and engineering talent. Industry trends followed suit. Many aerospace contractors pivoted their bids towards shuttle hardware when they saw it becoming NASA's favored post-Apollo vehicle. The skill sets and design capacity that might have gone into solving the Air Tug scale and handling problems were being redirected into orbiter frame development, reusable engine projects, and booster segment recovery for the shuttle's solid rockets. The more those resources shifted, the harder it became to maintain a dedicated team exploring a giant rotorcraft whose entire utility depended on a rocket family already nearing retirement. There was also a strategic perception gap. The shuttle could be imagined as central to every future mission profile. The Air Tug, no matter how capable in theory, was bound to a single type of first stage. If that stage disappeared from service, so did the Air Tug's primary mission, as planning moved toward integrated vehicles without massive, disposable lower stages. the rationale for investing in its development evaporated. In that environment, the helicopter's engineering achievements on paper could not overcome the narrowing window for its use. Financial justification worked against it as well. The Air Tug's business case rested on recovering and reusing expensive boosters to offset its own operating costs. The shuttle's promise was to avoid separate recovery systems entirely by bringing the main vehicle back intact. Even if the shuttle's reusability proved more expensive in practice, its political value as an all-in-one solution was high. It eliminated the need for massive offshore platforms, specialized aviation support ships, and a unique airframe built solely for a single recovery role. Within NASA's planning documents of the time, the emphasis shifted toward an integrated reusable vehicle as the core of post-Apollo operations. This shift was not because mid-air recovery appeared unattainable. Studies showed it could probably be done, but because it lacked the reach, flexibility, and long-term political appeal of a spaceplane system. The shuttle's operational infrastructure could be tied to existing launch centers and airfields, making it easier to defend in budget negotiations. As shuttle development advanced, other recovery-focused concepts lost momentum. Funding streams once earmarked for experimental capture systems were absorbed into design work for shuttle launch stacks, heat-resistant tiles, and recovery methods for solid rocket boosters after ocean splashdown. That last element echoed the trade-offs of sea recovery the Air Tug had sought to avoid, but now it was one part of a wider system justified on the basis of multiple launches per year. The Air Tug itself never left the study phase. NASA retained the proposal in its archives, and technical data from its wind tunnel evaluations and mass handling simulations remained useful for teaching and occasional design reference. But without a clear role in the evolving launch architecture, no budget line supported advancing it beyond paper. By the early 1970s, active work had ended, and the project existed mostly as a reminder of the Apollo era's willingness to consider extreme engineering to solve mission needs. The forces behind that outcome were as political as they were technical. Shuttle advocates could point to broader mission compatibility, easily understood operation, and a sleek, forward-looking image. The Air Tug's advantage applied to a shrinking set of launch scenarios. In the zero-sum environment of post-Apollo funding, those optics and the shuttle's larger mission envelope carried the day, leaving Air Tug studies without the sponsorship or funding they needed to continue. With the shuttle's promise and changing budgets, the mid-air recovery idea lost political and financial oxygen. So Hiller's concept faded into archived studies. Yet its core premise, that airborne interception could avoid the losses and limitations of ocean recovery, never entirely disappeared from Hiller's thinking, even as the giant helicopter proposal went quiet. A second try, rotor blades inside boosters. When the Air Tug proposal faded from active consideration, Stan Hiller explored a different angle on the recovery problem. Rather than sending a massive helicopter to meet a falling booster, he considered whether the booster itself could generate lift on the way down. The concept took shape as a variant with folding rotor blades stowed within the stage, deployed immediately after separation to auto-rotate and slow descent. In this approach, the upper portion of the booster would conceal a set of long, rigid blades hinged at their root. During launch, they would lie folded flat against the structure and be shielded behind aerodynamic panels to protect them from heat, vibration, and high-speed airflow. Once the main engines shut down and the stage detached, small mechanical releases or charge-driven actuators would open the panels, swing the blades outward, and lock them in position. As the booster fell, the upward flow of air through the spinning rotor would keep it turning without engine power, producing lift through auto-rotation and reducing the rate of descent. In theory, housing the recovery system inside the booster eliminated the need for a giant retrieval aircraft, along with its complicated staging from sea-based platforms. It also offered the possibility of avoiding saltwater contact entirely, if the auto-rotating stage could descend slowly enough to be managed over land, or lowered into calm water with minimal impact forces. Touching down intact could shorten refurbishment work and preserve more of the stage hardware for possible reuse. The technical requirements for such a system were demanding. To generate meaningful lift, for a stage that could exceed 100,000 pounds after fuel depletion. The rotor blades would still need to be exceptionally long even when folded. Each blade would have to deploy cleanly and lock under conditions of wind shear and dynamic motion. Once turning, they would experience enormous centrifugal loads at the hub and varying aerodynamic forces along their span. These loads demanded strong, heavy construction, but every kilogram devoted to the rotors, hinges, locks, and internal reinforcement displaced mass that could otherwise be used for payload. Weight penalties quickly emerged as the central trade-off. Launch vehicles operate within very tight mass margins, and hardware added for recovery directly reduces capability to orbit. Designing blades light enough not to consume that margin, yet strong enough to survive rotation at descent speeds, meant walking an engineering tightrope. Heavier blades would also require stronger attachment structures in the booster's top end, adding more material far from the stage's center of mass. Keeping the configuration stable during descent presented an entirely separate challenge. Helicopter fuselages are engineered to keep their center of gravity and rotor hub lift in precise alignment. A spent rocket stage, by contrast, is a long, mostly empty cylinder with dense mass concentrated toward the engine section at one end. With rotors mounted far above the center of mass, there was a risk of swinging, tumbling, or slowly tipping into a sideways descent. Without control surfaces to counter these tendencies, the stage could drift unpredictably, making the descent path and touchdown point difficult to control. The last few seconds before landing were perhaps the hardest part of the problem. Auto-rotation in a helicopter ends with a flare maneuver to bleed off vertical speed and cushion touchdown. But a booster-turned rotorcraft would have no pilot input or movable surfaces to perform such a maneuver. Even with lift slowing it most of the way down, the final impact speed could remain beyond what the lower structure and engine bay could handle. Additional deceleration aids, such as deployable legs or small retro rockets, would be needed to absorb the remaining energy, adding still more mass and complexity. These factors meant that even if the rotor system were perfected, it would exist in direct tension with the booster's primary mission. Any payload loss had to be offset by large financial savings from reuse, and the engineering path to that balance was uncertain. The integration work itself posed risks in other areas. Cutting into the booster's upper body to accommodate the folded blades and deployment panels would mean redesigning its load paths and strengthening those sections to survive ascent forces. Additional reinforcement would mean more weight in areas that already had to withstand intense aerodynamic and vibrational loads during launch. Some limited small-scale trials examined the physics of the idea. Lightweight drop test models, matching the proportions and mass distribution of a booster segment, were fitted with proportionally scaled rotors. In these tests, clean blade deployment allowed the model to auto-rotate steadily and descend more slowly than with parachute systems of similar mass. In calm air, these models landed in a stable vertical attitude without catastrophic stress to their lightweight frames. These tests offered encouraging data, but they were strictly at model scale. Small-scale auto-rotation results cannot be directly translated to full-size rocketry without accounting for scaling effects. Lift production does not increase linearly with size, while stresses from centrifugal force and aerodynamic loading rise steeply with both rotor length and rotational speed. Structural elements robust enough for a full-size booster could make the system too heavy to justify, erasing the mass benefit of removing dedicated recovery aircraft. Operating procedures also remained a hurdle. Even under rotor control, any large falling stage would need a clear and wide area for touchdown, free of obstructions that could catch the blades or tip the body. Steering a powerless stage toward such an area would require some form of control input during descent, increasing system complexity again. Over land, an off-target landing could pose safety hazards. Over water, even a softened impact would require quick recovery to prevent capsizing or waves damaging the hardware. Ultimately, this onboard rotor concept ran into the same fundamental constraints that had plagued the Air Tug. High mass penalties, structural demands that intensified with scale, uncertain controllability during descent, and engineering priorities already moving elsewhere. The project reached the point of demonstrating that at small scale, auto-rotation could lower descent rates and keep a stage upright. But bridging that gap to a full Saturn-class vehicle within acceptable payload and cost limits was another question entirely. Hiller's integrated rotor recovery remained intriguing on paper and in miniature trials, yet never advanced toward hardware-ready scale. NASA's attention and budgets were increasingly locked into systems that bypassed recovery aircraft altogether, aiming instead at launch vehicles designed to return intact under their own power. Hiller's onboard rotor variant produced promising small-scale data, but ran into the same scaling and mass penalty issues that doomed the Air Tug. And by this point, the agency's focus was elsewhere. Those limits mattered, because within a few decades, a different approach to booster reuse would emerge, one guided not by auto-rotation or mid-air capture, but by a propulsion-driven return profile that changed the economics of recovery altogether. 2025 Reality Check: SpaceX versus Air Tug. By 2025, booster recovery works on principles that would have been far out of reach in the 1960s. SpaceX's Falcon 9 first stages returned to either a ground pad near the launch site or a floating drone ship station downrange, using engine reignition, grid fins, and precision guidance to control their descent from separation all the way to touchdown. Starship's Super Heavy booster, in its early operational phase, is intended to guide itself into the embrace of mechanical arms fixed to a launch tower after executing a planned, powered descent. In all cases, the booster remains under its own powered control until it stops moving. There is no reliance on parachutes, mid-air capture aircraft, or uncontrolled drift. The Air Tug was built around the opposite idea. In that concept, the booster's descent would be mostly passive after stage. Separation slowed and oriented by parachutes. The helicopter would maneuver into position, match the booster's motion, latch on, and provide the lifting power to carry it back. Stabilization, steering, and the return trip all depended on the recovery aircraft. SpaceX avoids this by keeping every stage active. The vehicle itself absorbs the work the Air Tug would have had to do externally, so there is no separate heavy lift craft or remote position platform in the chain. The technological gap between these approaches is stark. For a Saturn-class first stage in the 1960s, the avionics of the time couldn't provide rapid, continuous adjustments during a high-energy descent. Onboard computers were bulky, heavy, and limited in processing power. They could not handle dynamic trajectory prediction, fast control feedback, or stabilizing inputs under varying wind and pressure conditions. Similarly, the F1 engines on the Saturn V were optimized for maximum thrust in ascent, not for restarting, throttling, or extending burn times in small increments. Adding those capabilities would have meant redesigning valves, turbopumps, ignition systems, and cooling, adding mass to a stage already pushed to its structural and performance limits. Without precise throttling or restart, a Saturn-class booster could not safely slow itself enough to land intact, which is why mid-air recovery or ocean retrieval were the only conceivable options then. Falcon 9's landing profile is supported by compact, lightweight computing hardware running control loops dozens of times per second. Combined data from GPS, inertial measurement units, and laser or radar altimeters flows into algorithms that constantly adjust engine gimbal positions, grid fin deflections, and throttle settings. This makes it possible for a booster to steer itself through changing winds, hit a target the size of a landing pad or drone ship deck, and do so without manual piloting. The Air Tug approach required human crews in the recovery craft to make these alignment corrections during the final descent, constrained by the physical limits and delay of moving a massive helicopter into position. Propulsive landing also simplifies operations. A Falcon booster lands near the launch site or on a ship already stationed along its predicted path. The only major moving asset at sea is that recovery ship, which functions as a floating platform and transporter. There is no need for a helicopter with extreme lift capacity, no separate base for refueling and maintenance positioned hundreds of miles offshore, and no intercept choreography in the middle of descent. The controlled landing converges the booster and recovery crew at the same fixed spot, rather than trying to bring them together mid-air. When comparing the economics The difference in infrastructure stands out more than any single dollar figure. Industry and public estimates for SpaceX's internal per-launch costs vary widely. Background reporting has cited ranges from about $15 million to $28 million for a Falcon 9, with the expendable second stage production alone estimated at around $12 million. By reusing boosters, SpaceX reduces the cost burden per launch compared to building new first stages for every flight. That reduction compounds over multiple flights of the same hardware. The Air Tug, in contrast, would have needed its own dedicated operating base, a large circle of trained crew for both flight and maintenance, and constant readiness of a platform physically large enough to support the helicopter's size and weight offshore. Research into its logistics concluded that the expense of keeping such a system active would have eaten heavily into any savings from stage recovery. Weather tolerance is another dividing line. Falcon 9 has landed successfully in a variety of conditions, including variable winds and different payload mass situations, maintaining consistent recovery rates in normal operations. While technical issues and bad weather can still force a return-to-sea landing or result in a failed recovery, most planned landings succeed. The Air Tug's performance projections, based on simulations, drop significantly in crosswinds or unstable canopy behavior during descent. Since actual booster falls would rarely occur in perfectly calm conditions, average case recovery rates might have been low enough to further weaken its cost-benefit equation. Autonomy also shifts the reliability balance. Modern boosters fly themselves home without human control inputs beyond mission oversight. That lets them respond instantly to new sensor data, gusts, or off-trajectory drift. The Air Tug's concept required pilots to control both the recovery aircraft and the suspended load after capture. This not only heightened training requirements, but also meant operational success could vary depending on the crew and exact conditions on the day. Starship's planned Mechazilla tower catch blends elements of interception with the powered descent model. The mechanical arms are fixed to the launch tower and do not maneuver to meet the booster. Instead, the booster flies itself to the arms with extreme precision. That strategy keeps all moving parts, maintenance, and personnel at the launch complex itself, removing the need to deploy recovery craft downrange and avoiding the cost and risk of staging large aviation assets at sea. The Air Tug could never achieve this degree of consolidation. Its very purpose depended on moving the capture point to wherever the booster dropped. By 2025, the toolkit available to launch providers, restartable, throttleable engines, highly capable flight computers, autonomous guidance links to navigation sensors, has made powered recovery practical at large scale. The Air Tug was conceived there because those tools simply did not exist for the Saturn family rockets. The only workable option was to meet the stage partway through its fall. With today's hardware, the winning approach is to keep the booster in command of its own return from separation to landing. That shift eliminates the need for an airborne crane, a fleet of specialty platforms, or precise mid-air docking maneuvers, while controlling costs and reducing points of failure. Looking back, the Air Tug encapsulates a particular moment in aerospace when recovering massive rocket hardware seemed to demand equally massive aviation support. Today's systems have replaced that with integrated control and simpler infrastructure. The contrast between these methods underscores how feasibility can flip entirely with the arrival of new technology, leaving behind concepts that once seemed the only realistic path. And while the Air Tug itself remained a paper study, the work done on its requirements, limitations, and recovery sequences did not disappear with the project shelving, setting the stage for ideas that would resurface in very different forms. Lessons learned for reusable rocketry. Some of the most enduring outcomes from the Air Tug studies were not about the helicopter itself, but about how you solve the operational challenges around recovering a fast-falling, high-value stage. In trying to make mid-air capture of a Saturn-class booster even remotely plausible, Hiller's team had to address two core problems that still define recovery work today: how to predict and track a target's trajectory in real time, and how to keep a recovery asset in position and ready until the last possible moment. Those requirements and the solutions they drove filtered into later aerospace projects in forms far removed from a giant rotorcraft. The first of these legacies, tracking and interception planning, was central to the Air Tug's proposed mission. The helicopter's crew would only have a narrow altitude window, measured in seconds, to secure a booster once it entered the interception band. To even attempt that, they needed a continuous, precise picture of where the stage was, where it would be, and when it would arrive there. In the 1960s, that meant combining multiple data sources: radar tracking to establish position and velocity, optical sightings to confirm parachute deployment and orientation, and signals from simple beacons carried on the stage. None of these were perfectly reliable alone, so the concept hinged on blending their inputs to generate a descent profile that could be updated in real time. Those calculations were not a one-and-done exercise. They changed moment by moment. Winds at altitude, shifts in parachute drag, or slight changes in staging trajectory could pull the booster off its predicted fall line. The idea was to feed those variations into a constantly revised intercept plan, giving the Air Tug a steering solution that stayed accurate up to the point of engagement. It was, in effect, treating the recovery like an aerial docking problem. Two moving objects converging under time pressure, one of which was only partially controllable. That operational mindset is still visible today, even though the platforms look completely different. Modern reusable rockets make those trajectory corrections themselves, guided by GPS, inertial sensors, and onboard computing. Smaller autonomous recovery craft work the other way around, updating their own position in response to a drifting target. But the logic behind the prediction and update loop is the same. The second major legacy is the loiter and readiness doctrine. For the Air Tug, being able to wait at altitude close to the target corridor was as critical as being able to sprint in for the capture. Launches could slip within a window for minor reasons, or wind changes could shift the descent footprint. If the recovery aircraft had to make long repositioning runs after every delay or trajectory shift, fuel and time margins would disappear. Instead, the plan was to put it in a holding pattern near the most probable intercept zone, fully configured for capture, and maintain that posture until the booster arrived in range. Endurance was as important as speed. If you burned too much fuel waiting, you might have to abort even a clean intercept because you could not carry the stage home afterwards. This station-keeping requirement shaped both the Air Tug's design studies and its operating concept. The recovery crew had to be able to transition instantly from steady loiter to a precision approach, with the aircraft and all its systems ready for full-power maneuvering. That meant thinking hard about control responsiveness, sensor integration, and workload distribution, so that complex positioning decisions could be made quickly and acted on without delay. Today's aerial and maritime recovery craft, whether drones shadowing a falling fairing half or boats moving under parachutes, use scaled-down versions of the same approach. They get into position early, hold as much as they can without wasting their reserves, then act decisively in the short window when the hardware is within reach. Both of these operational ideas, continuous, data-driven intercept planning and sustained readiness in position, were refined under the Air Tug program because they were not optional. A miss on either one meant failure. This sharpened the methods behind them: how to merge disparate sensor inputs without delay, how to recognize when the target's motion had moved outside the safe capture envelope, how to pivot from waiting posture to engagement posture in seconds. These concepts later proved broadly useful because they apply far beyond enormous helicopters and rocket stages. They are now routine in everything from automated aerial refueling trials to unmanned airborne retrieval of test packages, because the physics and the timing challenges don't change just because the vehicle does. It's important to frame these as operational parallels, not as a documented chain from Hiller's drawings to someone else's computer code. Many modern recovery systems use the same operational concepts Hiller had to solve: continuous position updates and ready loiter near the predicted target path, even if the scale, sensors, and vehicles have little in common with a mid-1960S booster catcher. The hardware path is different, but the mission logic rhymes. Focusing on just these two legacies also makes it clear why even an unrealized project can influence later practice. Engineers working to the Air Tug's constraints had to innovate under very specific pressures: narrow intercept windows, uncooperative targets, and the need for near-instant response. The fixes they devised for those pressures, predictive tracking that updates in real time and persistent readiness positioned close to the action, turned out to be broadly adaptable. They reduce risk and improve efficiency in recovery operations of all kinds, and they become part of the basic playbook in modern aerospace, where moving objects have to be caught, guided, or met in motion. There is an intellectual payoff here for looking back at a project like this. Even failed megaprojects move the discipline forward because they force engineers to solve the peripheral problems others will later reuse. In the Air Tug's case, the helicopter itself was too big, too costly, and too specialized to survive the budget and policy changes of its time. But the thinking it required about guidance, positioning, and readiness has survived in forms that fit the tools and missions of later decades. Seen in that light, the Air Tug's value isn't just a curiosity about an extreme design that could not be built. It's an example of how the work done in pursuit of an unlikely goal can leave behind lasting, practical methods. Those methods still matter anywhere the job involves being in exactly the right place at exactly the right time, with no second chances once the window opens. And it's this connection between big, improbable ambitions and the useful debris they leave in the technical landscape that keeps its story relevant. Understanding where those enduring fragments come from also helps in seeing the pattern that recurs across aerospace. Ambitious recovery concepts, whether in the 1960s or today, often have to develop sophisticated handling of timing, location, and readiness just to have a chance. When the main idea doesn't make it, those refinements tend to survive because they are applicable in many other contexts. In that way, the Air Tug sits alongside other never-built projects as part of a quiet inheritance of techniques that have been stripped to their original scale and reused where they fit. That inheritance sets up the last point worth considering before putting the Air Tug back into history. Its achievements exist in supporting methods, not in physical metal. The giant capture helicopter never flew, but the operational reasoning it pushed forward about how to find, position for, and meet a target on the move is part of the foundation for recovery work that does succeed today. And that makes it more than just an anecdote. It makes it a case study in how ambition can shape practice even when the flagship goal fades away. This perspective leads directly into a final view of what the Air Tug represents in the wider timeline of spaceflight ambitions and the limits of the technology of its time. The Air Tug stands as a reminder of how bold aerospace concepts can be, years ahead of the technology needed to make them real. It tackled the same fundamental challenge SpaceX solves today, but without the computing power, restartable engines, or precision control that now make propulsive landings routine. Its audacity was in trying to save hardware by meeting it in midair. The modern answer is to never let it fall uncontrolled in the first place. If you think a helicopter could have pulled it off, or have another wild recovery idea worth exploring, share your thoughts in the comments.